If you return to very early in the course, we talked about how there was two types of data, the two Qs, qualitative and quantitative data. Well, it turns out that for much of the course so far, we've been using mean as a way to analyze samples of quantitative data. And of course, we've now created this whole concept of a sampling distribution of sample means as yet another way to look at quantitative data. But the one thing we haven't covered a lot of is how we analyze qualitative data. For example, let's go back to an earlier scenario in the book where there was a class of 40 students and I asked them their political party preference. And you ended up with some raw data, something like this, where you had to count out how many Republicans, Democrats, and others were represented in the classroom. And what did we do with that data? We put it in a frequency distribution where we listed out the classes over here, which were the outcomes that we could get. And we ended up with how many there were for each of those political party preferences. You'll notice here that this is actually qualitative data. It's non-numeric. So the question of the day is if we have a sampling distribution for sample means, that's great and everything, but how are we going to actually deal with qualitative data? Well, it turns out that there's an entirely different sampling distribution that we can use in order to deal with qualitative data. And to just preview that, think about what's going on here with our frequency distribution. Remember, what's the next logical step here? The 21, 16, and 3 are great, but usually people like to see percentages, or in this case, relative frequencies. So a lot of you, in the beginning here, we took frequencies and we turned them into relative frequencies. So example, there's 40, right? So we would take 21 divided by 40 and we would get this value, and do the same for 16 over 40 and 3 over 40 and get the values over there. They were called relative frequencies, but another term for that is proportion. So while means are our main way of managing and dealing with quantitative data, proportions are going to be now the way of dealing with qualitative data. They're each going to have their own distributions. If you recall, for means, we needed two different variables. Why? Because we needed one that represented the population of all, that was the parameter mu, and we needed one that represented the sample, which was x bar. We, of course, knew that we often used x bar as a way to estimate what mu was, because mu was very difficult to calculate. And as a matter of fact, in statistics, we just don't compute mu. We use x bar as an estimator of it. We now need the same scenario or setup for proportions. We need a parameter, which we will call very conveniently P for proportion. That will represent the proportion of everyone that has a certain characteristic in the population. But then we need a variable that represents if we take a sample and we needed that proportion of the that has a certain characteristic. That will be called P hat. P hat. Note that P hat is actually defined as very simply x over n, where n is the sample size and x is the number having a certain characteristic. This is not meant to be something that is confusing. Of course, all you have to do is look at our example up here, right? Where we had, if I wanted to know the proportion, that is the proportion that are Republican. So how do I get that? X over n. What was x? X was the number having that characteristic. In other words, that are Republican, over the sample size in which we are dealing with. So 21 out of 40 gave us 0.525. So very simple stuff, but that is what p hat is equal to in terms of this. Okay, so just a quick example to here and make sure folks are following. It says, suppose it is known that 42% of all Americans who vacation during the summer will choose to work during their vacation. A survey is then conducted of 1,500 adult Americans who were asked whether they work while on summer vacation, and 690 indicated they plan to do so. Find the population and sample proportions of individuals who surveyed who plan to work on summer vacation. Okay, so again, just remember that the population proportion is P and the sample proportion is P hat. That is all they're looking for here. So you're looking into the problem and you're trying to pick out which one's which. So if it says, suppose it's known that 42% of all Americans who vacation choose to work, well, that would clearly be the population parameter P. So P is going to be equal to 0.42. Whereas the sample proportion is going to be the proportion that comes from some sample. Well, if a survey is conducted with 1,500 Americans and 690 indicated that they will work during vacation, then we're using our formula x over n right here. So we're just getting 690 out of 1,500, which is going to give us 0.46. And similar to how the sample mean was often not the same as the population mean, it's the same thing here. 42% are known to, or 0.42, whereas the sample yielded 0.46, or 46% of Americans choose to work during their summer vacation. So now that you know the variables involved with proportions and how we're going to deploy them, we now need to get into the sampling distribution of the sample proportion p hat. That is our goal here. So what I'm doing is I'm going to set this up in a very similar manner than I did to the theoretical example in sampling distributions of sample means. So this is going to be our population, our variable of interest, let's say would be, so just as a reminder, when we're doing a sampling distribution, we have our population and we take sample after sample after sample, of people, of certain amount of people from our population. So if you recall last time, we had the variable interest was height. What did we do for the distribution of sample means? We took the mean height from each one of these samples over and over and over again. They likely will be different. They could be the same, but likely different. And we eventually formed our own distribution of X bars. Well, now we have a little bit different scenario. Now our variable of interest is political party preference. So we're not interested in the mean. That does not apply here. We're interested in the proportion of folks that, let's say, are Republican, just as an example. So what we would do, we would go to our first sample and we would say, what is our p hat, our sample proportion of folks that are Republican? We would go to our next sample and say, well, what is our p hat for this? What is our p hat for the next one? And again, ... we would just keep on going, forming more and more p hats, or sample proportions, taken from all of these samples. So what do we do with these p hats? Well, just like last time, we're going to form a distribution. We're going to throw a p hat in here. We're going to throw another one in, let's say. We're going to throw another one in, and then so forth. And eventually what's going to happen is we're going to create a distribution. We call this the sampling distribution of the sample proportion. Think of it as a distribution that is filled with p hats. So in other words, p hats instead of x bars like last time. So lots and lots of p hats everywhere. Okay, so moving on, let's talk about sample proportions and how they compare to sample means. You've seen a diagram like this before. As a matter of fact, it was populations versus sample means, which was a great way to introduce the formulas for sample means. Well, we're going to do the same thing here, except we're going to use sample means to introduce the formulas for sample proportions. Okay, first things first, we have our graph of our sample mean, if you recall. Something like this. We had the middle was the mean of x bar, right? And the mean of x bar, our sample mean here, sampling distribution of the sample mean, was always equal to the population mean. Very straightforward. We had the standard deviation of our sampling distribution of the sample mean was equal to the population standard deviation divided by root n. And then our z value was taking an x bar. Remember that this distribution is filled with x bars, the sample mean of this sampling distribution. So we subtracted our mean and we divided by our standard deviation for our distribution in order to standardize. One last thing, remember that one of the key elements of a sample mean was ensuring that n was greater than or equal to 30 if the original distribution was not normal. And a lot of times they don't tell you that. So this comes up a lot in these scenarios, that n has to be greater than or equal to 30. One of the key differences between sampling distributions of sample means versus sample proportions is the type of material or given information that is provided to you in example problems. For distribution of sample means, you've already seen it. The key variables that are always provided are going to be mu and sigma, our population mean and standard deviation. So you're always going to get these, basically. In sample proportions, it's a whole different scenario. Now that we're dealing with qualitative data, the key variables are going to be n and p. In other words, you will be given the number of people that were asked whether they have a certain characteristic, as well as the population proportion of people that do. So what would be the equivalent of n greater than or equal to 30 for sample proportions? Believe it or not, it's going to be n times p times 1 minus p is greater than or equal to 10. We will use this as a way of determining normality in terms of any sample proportion problem. We'll talk about an example of that in a second. So assuming that that is met, then we again have our graph. Remember that this graph is going to be filled with p hats this time, a bunch of sample proportions everywhere. So no longer x bars, but p hats. We're going to need a center, so we're going to need the mean of p hat. That is going to end up right in the center there. Okay, so what is the mean of p hat going to be equal to in this scenario? Well, that is always going to be equal to the population proportion p. Remember, that is one of the variables that is given. What about the standard deviation of the population proportion? This is going to be a lot different. This is going to be equal to the square root of p times 1 minus p over n. Again, what variables are given in the problem? P and n. So this is going to be pretty straightforward to find. You're just going to plug them in to the formula in order to get the mean and standard deviation of the sampling distribution of the sample proportion. And lastly, what is our standardizing component? In other words, what is our z value when we want to standardize? So just generically, what are we always doing? We're taking the value we need to standardize. So what is our distribution made up of? Well, here it was x bars. Here it's going to be p hats. So that means we know that we are going to start with our p hat. We always subtract the mean of our distribution, which is basically here, our p. So yes, we're going to be subtracting p hat minus p in our numerator. The denominator is always going to be this value, which is going to be the square root of p times 1 minus p over n. If you follow it, it makes a lot of sense. We have whatever's in the distribution minus the mean over the standard deviation. Here, we have whatever's in the distribution, our p hats, minus our mean over our standard deviation. It's all the same stuff. It's just that the formula looks very different. But that's going to be the standardized formula that we're going to be using for this. Okay, so we've covered a lot of basically theory and formula work. So let's get to those examples to make sure this can actually work in your head and you can apply it. So I'm going to leave this proportions at the top of the page so we can look at all the nice formulas. It says, based on a study conducted by the Gallup organization, 76% of Americans believe the state of moral values in the U.S. is getting worse. Suppose we obtain a simple random sample of n equals 60 Americans and ask them if this is true. First, what is the mean and standard deviation of the sampling distribution of the sample proportion p hat? Okay, so before we get started, just let's look at the given information, right? So what did they tell us? They said 76% of Americans believe the state of moral values is blah, 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 getting worse, right? So it's saying of Americans. It's not saying of a sample. So we already know that this is P. It also had a sample of n equals 60 Americans. So just as I had stated before, what was the given information? It was n and p. So we use n and p to develop the sampling distribution of the sample proportion, which we can use for analysis. So how do we do that? Well, first things first, we need to find the mean. Well, the mean of a sample proportion is always equal to p, which is just going to be 0.76. So the mean of this distribution, which we're going to develop, this distribution of sample proportions, is 0.76. The standard deviation, a little bit more involved, is going to be equal to the square root of p times 1 minus p over n. So we do a little bit of calculation work. We got 0.76 times 1 minus 0.76 over the sample size that we took, which is just right there. So if we do that, we're going to get approximately 0.055 as our standard deviation. So think of it this way. The center of our distribution is at 0.76. We have approximately a 5 or 6% spread each way to the inflection points. So 0.05 or 0.06, however you want to interpret that, would be to the right that way of 0.76 and to the left of that way to create our distribution. Very similar to means, except now we're dealing with decimal points instead when moving one way or the other from our mean. Next question, is the sampling distribution of p hat considered approximately normal? Well, this is where we need to head over here to this requirement, and we're going to say, well, is n times p times 1 minus p greater than or equal to 10? Well, let's find this value. So n is 60. We have our proportion as 0.76, and we have 1 minus 0.76, which would be basically success failure, similar to binomial. We find this value. It's going to be approximately 10.94, which is greater than or equal to 10. So therefore, we can say that this is going to be normal 0.76, 0.055, and that'll be our distribution that we're dealing with. So now that we fully know our sampling distribution of our sample proportion, how exactly do these problems present themselves in terms of probability? Well, here's an example. It says, find the probability that less than 62% of Americans believe the state of moral values in the U.S. is getting worse. Okay, so if you recall when we did sample means, it was always going to be the probability that X bar was some relation, like greater than 80 or less than 25 or something like that. Well, now it's no longer X bar that we're dealing with in our distribution, it's p hat, which means our probabilities are going to be related to p hat. Well, in this case, we're doing less than 62%, so we're finding the probability that p hat is less than 0.62. That is our goal in this specific problem. Before we get into actually finding the probability, let's just take a look at this distribution. Remember, this is called the sampling distribution of the sample proportion. We know that it is normal with a mean of 0.76, which means in the middle here, 0.76 will be the mean. And we know that the standard deviation is about 0.055. So if we left it in 3 decimal places, that means that we should be able to find at least an idea of where these standard deviation markers are going to be, just to give us some context in terms of this distribution. So we're going to add 0.055 to go up. So 0.815 would bring us here. We're going to subtract 0.055 to go down. So that would be about here. Note that this still doesn't cover our 0.62, so let's go down a little bit more. That doesn't do it, so let's go down one more, 0.595, which means we're basically dealing with 0.62, which is about somewhere in here, and we're looking for less than that. That area right here represents this. That's what we're looking for in this problem. Just as we did with sample means, we have to find a way to standardize this curve. So we have to take our 0.62 and we have to standardize that value. Now, remember, we have a new formula for doing so. It is right here. This formula is solely for proportions. So let me just recopy it over here. We got p hat, our sample proportion, minus our population proportion, p, over the square root of p times 1 minus p over n. If we take these values, our p hat is whatever value we're trying to standardize, which is this guy right here, 0.062. And we're subtracting our population proportion, which is 0.76. And we're dividing by the square root of our population proportion times 1 minus that same proportion over n. Just be really careful here. Sometimes students make the error of using the p hat in these two values over here. Remember, once you write the actual value you're trying to standardize, which is 0.62, you're not going to use it again in the problem. Okay, if you do the mathematics for this, you're going to get negative 2.54. So we now know that the probability that p hat is less than 0.62 is the same as the probability that z is less than negative 2.54. So all we did was we essentially turned this p hat curve into a z curve with 0 in the middle and negative 2.54 here. And we're looking for the area below that. Then everything becomes the same as it was before. We have the z distribution. We have the skills we need by just looking at the table. Here's our z table. We're looking up negative 2.54, which is going to give us 0.0055 as the area that we're looking for. So just as a summary, the key here is you're trying to get to the point where you know the content already. So you know the content once you convert it to a z. That's old material. So the key is in the beginning, learning the new content that will get you to the content you already know. Okay, let's try one more example. It says, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 such Americans, what is the probability of at least 12% having hearing trouble? Okay, so just perusing through this, we did say 15% of all Americans, so that is a population proportion. So that must be 0.15. We also mentioned there was a random sample of n equals 120 Americans. And it appears that we're looking for the probability of at least 12% having hearing trouble. So what does that look like? Well, that looks like we're dealing with a p hat. Remember, when we say at least, that means that value or more. So we're looking for greater than. We could say greater than or equal to or greater than. Remember, there is no area at any one value, so both of those mean the same in continuous random variables. But it looks like this is the focus of the problem. Note that there was no mention of normality in the original population, so we want to make sure that we check np1 minus p to see if that's greater than or equal to 10. We are going to get 120 times 0.12 times 1 minus 0.12. This is going to give us a value of 12.672, which we now know is creates a normal distribution because it's greater than 10. Just remember that a normal distribution in the world of sample proportions is going to be p for the mean, and it's going to be p times 1 minus p over n. Square root is going to be for the standard deviation. So what does that look like for us? That looks like our proportion 0.15 And then we're going to have 0.15 times 1 minus 0.15 all over our sample size, which is 120, and that'll put together our standard deviation. This will give us around 0.033. So what about our distribution here? Okay, so we have, this is going to be our sampling distribution of our sample proportion. We now know is centered at a mean of 0.15 and is going to go out approximately 3 percentage points each way for the standard deviation markers. But we don't really need to write that. We just need to find our value of p hat, 0.12. We'll throw it someplace over here. And we're looking for at least, so we're going above that. Our goal is to find this area. We have all the tools at our disposal to do so. All we have to do is find our z. We're going to take our value. Remember, this is p hat minus, since it's a new formula, and rewrite it. P hat minus p times 1 minus p over n. So the value we're trying to convert, 0.12. We're subtracting our 0.15. Remember, we use this value for the rest of the calculation for all the p's over 120. We already know that this entire denominator is about 3 percentage points, 0.033, but it's good to throw the whole thing in so there's no rounding involved, and we get a precise z. If we do so, if we throw this into the entire mechanism here, we're going to get negative 0.92. So basically our p hat curve, we're converting into a z curve where we get 0, negative 0.92, 0 at the middle here. So this is equivalent to the probability that z is greater than or equal to, doesn't matter if we write one or the other, negative 0.92. If we look up negative 0.92 in the table, it is going to give us the area below it. That'll end up being 0.1787. Therefore, we need to subtract from 1 because we're looking for the area above it. This will give us 0.8213.